They are familiar with the background knowledge of my work.
Yeah, maybe not. Okay. Good afternoon and welcome to Purdue University, the Computer Security Seminar hosted by CERIAS. Our speaker today is a postdoc, got his PhD from the National University of Singapore, has been here at Purdue for the last year working with Professor Elisa Bertino. So Dr. Jason Chow, his topic today will be publishing microdata with robust privacy guarantee. Jason?
Thank you. Good afternoon, everyone. In the following, I will give a talk about data privacy. At the beginning, please allow me to introduce a bit about myself. My research interests are data privacy, access control, private record matching, and outsourcing data. My publications appear in top conference and top journals such as PFieldDB, TSEC, and FieldDB Journal. Today, the talk of today will be about data privacy. Let me first introduce some background knowledge. Government agencies and hospitals need to regularly release data for the benefits of public and for the purpose of research. However, to protect the privacy of individuals, the identity information such as name, phone number are removed from the data before they are published. However, if we release such data, then the privacy of individuals will still be violated. For example, the table without the identity can still be linked to the voter registration list. Voter registration list is kind of some external public database. These two tables can be linked by age, sex, and zip code. In such a way, we can identify the disease of Bob. We can see that Bob suffers from bronchitis. In data privacy, we call attributes such as age, sex, and zip code quasi-identifier. And such kind of attributes can be linked to external database such as voter registration list to re-identify individuals. We name attribute such as disease as a sensitive attribute. The values of such attribute are not supposed to be disclosed. Otherwise, sensitive personal information about individuals will be disclosed. To address the link attack I just mentioned above, what we do is that we first partition the data into groups. We call each group an equivalence class. For example, here we have two equivalence class, equivalence class 1 and equivalence class 2. After we partition the data into equivalence classes, we then generalize the quasi-identifier values in each class. For example, here in equivalence class 1, we generalize the age value to 26 and 27. Since all the tuples in equivalence class 1 has a male value, so the sex value is not generalized. And we also do a generalization on the zip code value. Now, if we still do a linking attack, we will find that for example, Bob, it may be suffered from bronchitis, broken arm, or AIDS. So the information now is uncertain. However, since we do the generalization, therefore, we distort the values. And to measure such kind of distortion, we introduce some information loss matrix. Such kind of I give some intuition about such information loss matrix. We first consider each quasi-identifier attribute as one dimension. Here there are 3 dimensions: age, sex, and zip code. Then each tuple can be modeled as a point in this data space. And the equivalence class can be modeled as a minimum bounding box. When the minimum bounding box, the ranges of the minimum bounding box are bigger, then the distortion will be larger. And in our solutions, we will try to minimize the ranges of the minimum bounding box. Is everything clear so far? Okay. So do you have some knowledge about k-anonymity, L-diversity? Okay. So I will introduce. I will talk about, in this slide, I will talk about k-anonymity and L-diversity. K-anonymity is a concept introduced in 1998 by Striven in CMU. K-anonymity requires that in each equivalence class, there are at least k tuples. Here, each equivalence class has 3 tuples, so k here is equal to 3. That is to say, such kind of formation satisfies 3 anonymity. However, k-anonymity is prone to homogeneity attack. For example, here all the sensitive values, that is the disease, in equivalence class 2 are hepatitis. Therefore, once we know that a person is in this equivalence class, we are 100% sure that that particular person suffers from hepatitis. Therefore, L-diversity was introduced. L-diversity requires that in each equivalence class, there shall be at least L well-represented SA values. However, L-diversity still suffers from some attacks. The first attack is called Skewness Attack. I give an example here. In the whole database, it is possible that the percentage of persons infected with HIV is 0.1%. Now, suppose that we form an equivalence class satisfy 10 diversity. 10 in the research community of L-diversity is supposed to be big. So by L-diversity matrix, it is supposed that the privacy guarantee is high. However, we know that if an equivalence class contains 10 different sensitive values, each occurs only once, then we still know that any particular person in this equivalence class is infected with HIV with a probability of 10%. Such kind of information gain from 0.1% to 10% is actually still fairly big. It is a 100-fold increase. is here clear? Okay, I should continue just. L diversity also suffers from similarity attack. Here in equivalence class 1, there are 3 different sensitive values. However, each sensitive value is just a case of respiratory problem. Therefore, even we don't know therefore we can still know that a person in the equivalence class 1 suffers from respiratory problem. To address the above 2 attacks, such kind of attack is actually because of the it's because L diversity does not consider the unavoidable background knowledge, that is the global distribution of the sensitive attribute in the whole table. To address such kind of limitations of L diversity, T-closeness has been proposed. T-closeness model was proposed by Professor Ninghui Li in Purdue University in 2007. They consider the sensitive attribute value domain v1, v2, vm. That is to say, altogether we have m sensitive attribute values from v1, v2 to vm. And since we publish the whole table, therefore, the global distribution of the sensitive values P1, P2 to PM is the public knowledge. Here, P1 is the global distribution of sensitive value V1, P2 is for V2, and PM is for VM. And now, if we publish data by equivalence class, in each equivalence class, there's also the distribution of the sensitive attribute. Let's assume that such a distribution is equal to Q1, Q2, and Qa. Therefore, now we have 2 distributions: the global distribution, big P, and the local distribution in an equivalence class Q. So we would like to minimize the difference of these 2 distributions to limit the information leak, and to evaluate the distance between the 2 distributions. They adopt Earth movers distance. Earth move distance takes the global distribution, big P, P1, P2 to PM, as a set of holes, and they take the local distribution Q1, Q2, and QM as a path of Earth. EMD requires that EMD is the minimum work to fill the sets of holes by the paths of Earth. However, based on our analysis, even T-closeness still has limitations, because EMD is actually an aggregator distance function. So it calculates the difference between big P and big Q. Given a T value, we actually don't know the individual difference between Pj and Qj. In such a way, we cannot translate T into any clear privacy guarantee. Do you have some questions? So maybe you do not understand what I'm talking about. I give an example to illustrate to illustrate the limitation of T closeness. Suppose there are two sensitive values, HIV and flu. In the case 1, the global distribution of HIV and flu is 0.4 and 0.6. That is to say, in the whole database, 40% persons are affected with HIV, 60% of them are affected with flu. Let's consider an equivalence class. Suppose that the distribution in the equivalence class is half and half. In case 2, the global distribution of HIV is 0.01 and the flu is 0.99. And the Q prime is the local distribution in an equivalence class. By the EMD matrix of T closeness, the distance between P and Q and the light between P prime and Q prime are both 0.1. So by T closeness, these two cases provide the same privacy level or the same privacy guarantee. However, if we consider the relative distance between 0.4 and 0.5, we know that from 0.4 to 0.5, the rise is 25%. However, in the case 2, from 0.01 to 0.11, the probability of HIV rises is 1000%. So actually, the case 2 provide a much lower privacy guarantee. However, by T closeness, they are the same. To address such kind of limitation of T closeness, we then introduce bit likeness. Still, let's consider the sensitive attribute domain, that is V1, V2, Vi to Vm. And suppose that P is the global distribution of the sensitive attribute, and Q is the sensitive attribute distribution in an equivalence class. Based on our analysis, we first consider if the global distribution, consider a case that the global distribution is smaller than the local distribution. For such kind of case, actually, the correlation between a person and the sensitive value Vi is lower in an equivalence class. Therefore, actually, the privacy guarantee is higher. So, we only focus on the case that Qi is larger than Pi. That is to say, the distribution of sensitive value Vi in an equivalence class is bigger than that in the whole dataset. And our matrix of bit likeness requires that the distance of every Pi and Qi is smaller or equal, is smaller than or equal to beta. Here, I only talked about the distance, but there can be a lot of distance functions. In the following, I will introduce the distance function to be used for our model. The first fairly simple distance function is the absolute difference. That is, qi minus pi smaller than or equal to beta. However, let's assume that beta is equal to 0.2 and the pi, the global distribution of sensitive value phi is 0.01. By the distance function, we know that qi can be as large as 0.21. From 0.01 to 0.21, the increase is actually 20-fold. So the difference is very big. The conclusion is that we should not use such kind of absolute distance function. Therefore, we consider relative distance. By such kind of relative distance function, we can reach this inequality, and this equality will be meaningful only when pi is smaller than 1 of 1 plus beta, because when pi is larger than 1 of 1 plus beta, then qi can be as big as 1. If qi is equal to 1, then in an equivalence class, all the sensitive values of all the tuples will be the same value, and the privacy of the users would be disclosed. So we come to the third attempt. Our distance function now is designed in this way, and by some simple transformation, we can reach this formula. In the following, I will analyze the properties of this formula. First, if the input parameter pi is smaller than 1, then the function value will be always smaller than 1. And this function f has the property of monotonicity. That is to say, if given two values, pi and pj, if pi is smaller than pj, then fpi will be smaller than fpj. For infrequent sensitive values, its distribution in an equivalence class can be increased by beta times. But for frequent sensitive values, its increase will be much smaller. It will be smaller than beta times. So far, we have the privacy matrix beta likeness, and we introduced our distance function to satisfy beta likeness. However, we still need some algorithm to release the data so that beta likeness will be satisfied. In the following, I will talk about the algorithms to satisfy beta likeness. Our algorithm was designed based on an observation. Here, there are two quasi-identifier attributes, age and weight. If we take age as one dimension and the weight as a second one, then each tuple can be seen as a point in this data space. Here there are 6 data points, and each data point has a different sensitive values, has a different disease. We use different shapes to represent the disease. For example, it is SARS, it is pneumonia, and so on. To satisfy zero likeness, that is beta is equal to 0, then we need to take all the tuples. We need to take all the tuples and form a single equivalence class. In such a way, the data, the released data will be generalized and distorted and the information quality of the released data will be very low. If you remember, I mentioned at the beginning of the talk, we would like to minimize the minimum bounding box of each equivalence class to minimize the distortion of the released data. So what we do, we first partition the data to buckets so that all the sensitive value, all the tuples with the same sensitive value will only be in one bucket. In this example, the first two sensitive values and their tuples will be in bucket 1. The middle two are in bucket 2, and the last two are in the last bucket. And now, if we take one tuple from each bucket and form an equivalence class of them, we will have two equivalence classes. Here, it is obvious that the minimum bounding box of each equivalence class is much smaller. In such a way, the distortion of the released data is smaller, so we preserve more information. However, such kind of formation will not satisfy zero likeness. So actually, we trade the privacy for the data utility. Actually, in the research of data privacy, we always have a trade-off between the data utility and the privacy. Does anyone have a question? But do you understand what I'm talking about? If you can understand from a high level, then it's maybe you also get some information from my talk. If you do not understand anything, then it's too bad. So, based on the above observation, we propose a scheme or an algorithm. Here there are 3 buckets and altogether 19 tuples. SARS and pneumonia in the first bucket. 3 tuples with bronchitis are in the second bucket. The 3 tuples with hepatitis are also in the second bucket. Gastric ulcer and intestinal cancers are in the third bucket. We can take from each bucket some tuples to form an equivalence class. We can take x1 tuples from bucket 1, x2 tuples from bucket 2, and x3 tuples from bucket 3 to form an equivalence class. In the worst case, let's consider that the xi tuples from bucket bi are not frequent or least frequent. We use VIL to represent the least frequent sensitive value from bucket I. And from this worst case, we developed a theorem. It is called eligibility condition, this inequality. This inequality has some intuition. That is, since we take xi tuples from bucket bi, and suppose that vi is a sensitive value in bucket bi, so the distribution of phi j in the equivalence class G will be at most this value. And by the eligibility condition, we know that this part holds. And since the function has the property of monotonicity, so this inequality also holds because pi is bigger than PIL. PIL is the least frequent sensitive value in bucket BI. Therefore, this whole formula folds, and once Qj smaller than fpj, bit likeness is satisfied. In brief, we can use the eligibility condition to check the bit likeness in each equivalence class to see whether bit likeness is satisfied. However, the eligibility condition still does not tell us how to form the buckets. That is, what sensitive attribute values should be put into which bucket. It is not clear. Therefore, what we do is as follows: we assume that when we take tuples from each bucket, it is proportional. That is to say, if we take xi tuples from bucket bi, then this value should be equal to the size of bucket bi over the whole database size. And this ratio is equal to this summation. Therefore, by replace xi, the absolute value, the cardinality of xi of the cardinality of G, by this summation, we reach this formula. And by this formula, we can decide which sensitive values can be put into a single bucket. In our paper, which appeared in FieldDB 2012, we use dynamic programming to partition the sensitive values into buckets. In this example, we altogether has 19 tuples. The global distribution of SARS is equal to 2 over 19, and that of pneumonia is equal to 3 over 19. Their summation will be this side, and the least frequent sensitive value in bucket 1 is SARS. So here FPIL will be equal to 2 over 19. That is the distribution of SARS. And since this formula holds, so SARS and pneumonia can be put into a single bucket. In a similar way, we can verify that bronchitis and hepatitis can also be put into a single bucket, and the remaining 2 sensitive attribute values can be put into bucket 3. So altogether, we have 3 buckets. after we form the buckets, then we need to decide how many tuples should be taken from each bucket to form an equivalence class. We call this step reallocation. Our scheme is called BURO. BU is from bucketization. REL is from reallocation. And after we decide how many tuples should be taken from each bucket, in the third step, we will consider how to minimize the information loss to take the tuples from bucket. That is, what kind of tuples with what kind of properties should be taken from each bucket to minimize the information loss. Here I still use the same example to show the determination of the equivalence classes. The number of the tuples in first bucket is 5, 6 is for the second bucket, and 8 is for the third bucket. What we do is that we split these values into 2, because in the last slide I talked about the proportionality requirement. We would like to take tuples from each bucket proportionally to the size of the buckets. When we do such kind of splitting, we need to check if the eligibility condition holds. If the eligibility condition holds, then we just split it. And such kind of splitting is done recursively. So finally, we will have 3 leaf nodes. Each node represents an equivalence class. For example, this one, the first leaf node on the leftmost, says that we can take one tuple, any tuple from bucket 1, any one tuple from bucket 2, and any 2 tuples from bucket 3. Any tuples you take, beta likeness will be satisfied. Here, the beta is equal to 2. And since we would like to minimize the information loss in the third step, although we can take any one tuple from bucket 1, any one tuple from bucket 2, and any 2 tuples from bucket 3. However, usually we would like to find these 4 tuples which have very similar QI values in such a way when we use a minimum bounding box to bound their range. The ranges of the bounding box will be small and the distortion will be smaller. So the information loss will be small. In the above, BURO is a generalization-based approach. In our work, we have proposed a second one, which is based on perturbation. Why we propose perturbation? Because here is an example. Suppose that we have only 2 buckets. The first bucket contains 2 tuples. The second contains 10,000 tuples. Such case may happen in the real world because the sensitive values in bucket 1 may be fairly infrequent, but that in the second bucket can be fairly frequent. If we follow the proportionality requirement, we can form at most 2 equivalence classes. 1 tuple from first bucket and 5,000 tuples from the second bucket. Since the equivalence class is fairly big, with the size of 5,001 tuples, so the incurred information loss will also be fairly high. Such kind of observation motivated our second approach, that is, the approach based on perturbation. Our idea is actually still simple. We toss a coin. If it is head with the probability of alpha I, then we keep the sensitive value phi I unchanged. However, if it is tail with the probability 1 minus alpha I, then we use a randomly generated sensitive value to replace this phi I value. Such kind of high-level idea need to be supported by some theory to make sure that bit likeness is satisfied. Here we adopt low I1 to low I2 privacy. It is a privacy metric proposed by I don't know how to spell this last name. The work appeared in Purdue 2003. To cite here, row 1i, it is actually the prior knowledge. We can consider it, in our case, we can consider it as the global distribution. And row 1, 2 is equal to the posterior distribution. We can consider it as the distribution in an equivalence class. With such kind of correspondence, we can adopt low I1 to low I2 privacy to our model to ensure the privacy. But how to decide the relationship between alpha I and low I2? Please, if you are interested, please read our paper. It seems that I make you guys suffer a lot, so I will try to be fast. Now I'm talking about the experiment. In our experiment, we adopt a census dataset, which it is a real dataset containing 5.5 million tuples. It contains 5 quasi-identified attributes and 1 sensitive attribute. We first compare our proposed scheme with 2 T-closeness schemes. The first one is called SABA. SABA is actually a scheme proposed by us. T-Mondria, it is an approach proposed by Professor Ninghui Li and his student. Our comparison is composed of 3 parts. In the first part, different data. For the first part, we first vary the beta value. Given a beta value, we use Purdue to generate release the data. For each released equivalence class, we calculate its T-closeness, and the biggest T will be considered as T beta. In such a way, although our scheme is supposed to satisfy bit likeness, but at the same time, it also satisfies T beta closeness. So we compare our scheme with the other T closeness scheme by setting T equal to T beta. According to the experimental results, we can see that our approach, Purdue, always has the smallest beta value, real beta value. That is to say, our solution provides higher privacy guarantee. In the second case, for each t-closeness scheme given its t parameter, we generate a data set. For each scheme, we'll generate a data set, satisfy t-closeness, and then for that t value, and then for each equivalence class, we find its constraint on the beta likeness. Suppose that beta t is the highest beta value, or is the beta value satisfy the t closeness, and we compare the three schemes. We still find that Purdue outperforms the other two approaches clearly. And in the third part, we set all the schemes to have the same information loss, and then evaluate their privacy guarantee. In terms of beta likeness, we still find that Purdue is the winner. So, from this set of experiments, we actually show by experiment that our proposed scheme is more secure than the existing approaches, and at the same time, we provide higher utility. To make our approach more meaningful, we include more experiments. We developed two benchmarks. The first one is an extension from Jianneng, and the second one is an extension of delta disclosure based on the experiments. Our approach has the lowest information loss. AIL means average information loss, and our running time is the lowest offload. So, based on these experiments, we can claim that our scheme provides high utility data, and it is efficient. Conclusion. In this work, we have proposed a robust model for microdata anonymization. Our privacy guarantee is comprehensible. It is easy to understand because basically it evaluates the difference on each sensitive value. That's my talk. If you have any question, I will be happy to answer. My God. So you are totally lost.
I have a question.
Okay.
So how exactly can you make sure that it's robust to similarity attack when your buckets are chosen sort of automatically? Like, you might have a distribution of your buckets that include some sensitive attributes that are still in the same class, like there might be pneumonia and then some other respiratory illnesses, and then you might end up with an equivalence class that, since you minimize information loss, it still ends up with a lot of similarity. Or is that even possible, or did I misunderstand?
Yeah, it seems that you can catch my presentation. It is true. If the beta value is bigger, then it is possible that in an equivalence class, the sensitive attribute values will be semantically closer. For example, if we come here, here in equivalence class 1, all the tuples have the semantically close sensitive values. That is, they are all the cases of respiratory problems. If we make beta bigger, such as, for example, beta is equal to 4, then it is possible, even by beta likeness, in a formed class, in a formed equivalence class, these 3 values appear. So it is true. Actually, to ensure such kind of problem does not occur, we need to reduce the value of beta. So now still there's a trade-off between the data utility and privacy. And actually, for all the schemes, for all the privacy matrices such as k-anonymity, L-diversity, and T-closeness, and here beta likeness, if we impose a higher privacy requirement for T-closeness, we can require the value of k fairly big. In the worst case, it can be as big as the size of the whole data set. That is to say, the whole data set form a single equivalence class. For L diversity, we can require that L is equal to the domain size of the sensitive attribute. And for T closeness, we can require T equal to 0. For beta likeness, we can require beta equal to 0. In such a way, actually, all the privacy schemes and matrices will converge. But still, if we adopt such kind of naive approach, the information loss will be fairly high. Our work, the difference of our work, or the advantage of our work of T closeness is that our model can clearly specify the information gain. We specify that the information gain is from is the difference from pi and qi. But T closeness, it tells you that all the aggregated distance between all these values and all these values are T. So by T closeness, we are not sure, even we are given a fairly small T, whether the relative difference between pi and qi will be bigger. I have given an example here. Although by EMD, the T here equal to 0.1. However, not only the privacy guarantee of these two cases are different, but here the information leak or the information gain on the HIV is actually fairly big. So maybe I confused you. Does anyone else have a question? Okay, then my job is done. Thank you.